Welcome everyone to this talk about impact of climate change on the surface heat fluxes. My name is Ana Ayala. I am PhD student at Uppsala University and the University of Geneva, and I am part of MANTEL project. Over the past 100 years, climate has been changing and will continue to change. And lakes are already responding rapidly to this changing climate. Lake surface water temperature is getting warmer across the world, and this warming was most pronounced from 1980. Lake surface water temperature is influenced by climatic and inlet drivers that contribute to the lake surface energy budget, such as the incoming shockwave radiation, the incoming long-wave radiation, the proportion of solar irradiance absorbed at the lake surface, the advection and storage of heat within the lake, and the loss of heat at the air-water interface through outgoing long radiation and turbulent fluxes of sensible and latent heat. These drivers are affected by climate variables such as air temperature, wind speed, cloud cover, and atmospheric humidity. Changes in any of them can influence lake surface water temperature and ice cover through multiple feedback into surface energy balance. ECME aim is provide a comprehensive picture of climate change impact at different levels of global warming. That in 21st century, 3 different climate projections are available. RCP 2.6 in dark blue, in which carbon dioxide emissions start to decline by 2020 and go zero to 2100. This is the very stringent scenario, in which global temperature is projected to rise below 2,000 degrees by 2100. RCP 6.0 in yellow is the intermediate scenario, in which emissions peak around 2080. Global temperature rise between 3 and 4,000 degrees by 2100. RCP 8.5 in red is the worst case climate change scenario. The emissions continue to rise through the 21st century, and then the global temperature rise between 4 and 5,000 degrees by 2100. And in green, we can see the climate projection at pre-industrial levels. Hydrodynamic models are forth with this climate projection and allow us to evaluate the impacts on lakes. Here we can see the impact of climate change on the thermal structure for Lake Kärken in Sweden. Lake Kärken is a diminishing lake with a maximum depth of 21 meters and a surface area of 24 kilometers square. This picture shows the projected changes in surface temperature, water temperature, seismic stability, thermocline depth, duration, onset, and loss of stratification at the end of the 21st century for the future scenario RCP 6.0 under 4 different global climate models. In blue, the vertical line in blue are the mean, and the dashed line is the zero. This means no changes. The surface and water temperature are projected to increase on average 3 and 1 Celsius degree respectively. The seismic stability reveals that more energy is required to completely mix the water column. This greater stability also corresponds to 22 days longer duration of stratification, 14 days with an early onset, and 8 days with a later fall overtone, and a shallower thermocline depth. Most of the study had focused on how different thermal metrics change and the different levels of global warming. But little attention has been focused on the projected changes in surface heat fluxes. Simply model is used to evaluate changes in the surface heat fluxes in response to climate change in North Ireland. The lake model is formed by Pingat's corrected projection from ECM to B for 4 different global climate models and 3 future scenarios. The net heat flux at the surface is given by the sum of radiative fluxes in red and turbulent heat fluxes in blue. The heat fluxes from the atmosphere to the lake are defined to be positive when the lake gains heat, and negative when the lake emits heat. The short wave absorption is positive. The long wave absorption is positive. The long wave emission is negative. The latent heat flux is negative or positive, and the sensible heat flux is negative or positive. The short wave absorption is the amount of solar radiation that penetrates into the water. The incident solar radiation is partially reflected by the light surface and depends on the albedo. This figure shows the mean monthly shortwave absorption of the assembly from 2006 to 2099 for the RCP0.0 scenario. The shortwave absorption reached the maximum in May, June, July, and the minimum in winter. In summer, the variation of the daily shortwave absorption is higher than in winter. When comparing the monthly mean shortwave absorption for the 3 figure scenarios and the pre-industrial condition, we can see that the shortwave absorption for the future projection are slightly lower than the pre-industrial condition than in the summer. The long wave radiation that enter to the water body depend on atmospheric humidity, clouds, and temperature. The long wave absorption reached the maximum in July, August, and the minimum in winter. The variation of the daily long wave absorption is the same in summer and winter. The long wave absorption for the future projections are greater than the pre-industrial condition. These changes are slightly higher in summer than in winter. The long wave emission is proportional to the surface water temperature to the power 4. The greater heat loss occurs when the surface water temperature is higher in summer. The variability of long wave emission is greater in summer than in winter. Our heat loss for the future projection are greater than the pre-industrial condition, as well as the future projection of the surface water temperature. The latent heat flux depends on the difference between the saturated water vapor pressure and the water vapor pressure for the air over the lake, and the transference function, which depends on the water temperature difference and wind speed. So the latent heat flux depends on the size of the lake or wind fetch. If saturated water vapor pressure is lower than the water vapor pressure for the air, there is condensation. This happens in winter. Most of the year, the saturated water vapor pressure is greater than the water vapor pressure for the air, so there is evaporation. The monthly mean maximum heat loss by evaporation is in the summer, and the lowest heat by evaporation is in winter. For the future projection, evaporated heat loss tend to increase compared to pre-industrial conditions, with the greater changes than in the summer. The flux of sensible heat is the smaller contribution to the heat balance. The sensible heat flux depend on water temperature difference and also on surface fusion and Bowen coefficient. When the surface water temperature is greater than their temperature, the light surface loses heat. However, when the surface water temperature is lower than their temperature, the light surface gains heat. The heat loss is maximum in summer and the heat gain is maximum in February-March. For the future projection, sensible heat flux tend to gain less heat in February and March and loses less heat from August to November compared to pre-industrial conditions. When we consider together all the components of surface heat fluxes, we can notice that the light surface gains heat from March to August and loses heat from September to February. When comparing future projection with pre-industrial conditions, we notice that from March to June, the light surface gains less heat, and from September to December, the light surface loses less heat. And these changes are of a similar magnitude. The trend in annual air temperature caused the trend in the mean annual surface water temperature. We expected to find a similar trend for next surface heat flux, but it has not been found. So, what about the heat fluxes? For here, we can see the average annual time series for sensible heat flux, latent heat flux, long-wave absorption, long-wave emission, and short-wave absorption for the three future projections in blue and the pre-industrial conditions in gray. The linear trends in the annual long-wave absorption and long-wave emission were significant. However, the linear trend in short-wave absorption was non-significant. Regarding the latent heat flux, the annual mean changed significantly. There was an increase of the heat loss. The sensible heat flux trends was significant for RCP 0.0, but not significant for RCP 8.5. Why is this happening? When the air temperature trend is of a similar magnitude to the surface water temperature trend, the water temperature difference shows no significant trend. However, when the air temperature trend is of a different magnitude to the surface water temperature trend, the water temperature difference shows a significant trend. So the linear trend in sensible heat flux is significant. The results show that increasing long-wave absorption was responsible for the light surface warming. Heat losses to the atmosphere along with emission and by latent heat flux have intensified due to the higher light surface temperature. Summarizing, incoming long-wave radiation increases the light surface water temperature, and the warmer surface water temperature emits more long-wave radiation and more water is evaporated. The next steps are to extend the analysis to 62 layers across the world with different geographical and morphological characteristics, and estimate the projected heat fluxes with other 1D lake models, GOTEN and GLA. Thank you for your attention.